Hi everyone, welcome back. In today's video, we are continuing with calculus in differentiation, but rather than kind of moving to more complex differentiation like we did last time doing implicit differentiation, this time we are actually using our differentiation skills and apply it to more contextual problems. And in this case, we are going to do motion. So before we get started, let's first get some basic idea of motion. So in motion, we have, perhaps when you think about this topic, maybe you think about distance, maybe you think about how fast an object is moving, or maybe perhaps the velocity, or maybe even where the particle or the object is located at. So if we want to find, for example, the position, that's called S of t, and we call that displacement, which basically means the position of a particle, displacement. And then next we have velocity, right? That's represented by v of t. And then we have a of t, and you guessed it right, it is the acceleration of a particle. So when we connect all of these together, basically when we want to move from displacement to velocity, basically we just take the derivative of displacement to get velocity. And if we want to go from velocity to acceleration, you guessed it right, we have to derive the velocity. So now that we have this basic summary of the idea of motion, let's apply it to an example. A particle moves in a straight line with position relative to O given by S of t equals to t cubed minus 6t squared plus 9t minus 1 cm, where t is the time in seconds. And you have to note that t has to be greater than or equal to 0. So part A, find expressions for the particle's velocity and acceleration and draw sign diagrams for each of them. So basically what we want to do is find v of t and a of t. And we know that v of t is basically the derivative of s of t. So to do that, let me just first copy down what s of t is. We know that s of t is t cubed minus 6t squared plus 9t minus 1. So now we want to find the velocity, and that's the derivative of s of t. So if we do that, we get 3t squared minus 12t plus 9. And if you have trouble doing this, I definitely recommend you to go back to one of my previous videos on introduction to differentiation, because that is really the basics of this whole problem here, because finding the derivative is basically what we're doing, and now we're just applying it. So definitely recommend that. I do have video on chain rule and implicit differentiation as well, but in this problem, we don't particularly need to know that. So just basic differentiation. Okay, so now we have a of t. And to find that, we basically do the velocity and we derive that. So the derivative of that is going to be 3 times 2 is 6t minus 12. And there you have it. Now we want to draw sign diagrams. So a sign diagram basically shows where it's positive and where it's negative. So for example, if I have a quadratic function, I want to know when it is positive and when it's negative. Well, it's positive when the x value is greater than 0, right? And it's negative when it's less than 0. But how do we do that? Well, we do that by finding where the roots are. And it is positive when it's above the roots, and it's negative when it's below the roots. So you probably guessed it right. When we do sign diagrams, we always want to find the zeros so that we know when it is positive and when it is negative. So basically, if we take that equal to 0 for velocity, well, in this case, it's a quadratic function, So maybe we can factor it. If we factor it, we get t minus 3 times t minus 1. And it is equal to 0 when t equals to 3 and t equals to 1. And if we were to draw a sign diagram for that, well, when we do sign diagrams, oftentimes we do open arrows on both ways. But here, notice how it says that t has to be greater than or equal to 0, because logically, time cannot be negative. So we have a limit there. It has to be greater than 0. And then now we're trying to find the sign diagram for velocity. And we found the roots, which is at 3 and 1. So if we were to draw a sign diagram, basically we want to find out when it is positive and when it is negative. One way you can do it is you can plot in numbers. So between 0 and 1, let's say I want to plot 1 over 2. So if I were to plot 1 over 2, my overall value would be positive, because negative times negative is going to be positive. And between 1 and 3, let's say I do 2. If I plug in 2 into the equation, I get negative times a positive number, and that's going to be a negative number. And last but not least, I plot any number between 3 and infinity. And let's say I choose 5, I get an overall positive value. That's one way you can do it. Another way you can do it is you can think about this logically or graphically. We know that this is going to be a quadratic function, and because the value a, 3, that is a positive number, we know that it is concave up. And the zeros are at, okay, I mean this doesn't really make sense because it's 1 and 3, let's say here. So we have the zeros at 3 and 1. We know that it's going to be positive when it's less than 1. We know that it's also going to be positive when it's greater than 3, shown here. And we know that it's negative between these two roots. And so we drew negative here. And that makes sense, right? Because a quadratic function. So that's another way you can do it. And now for this one, a of t, we want to set it equal to 0. And when we do that, we get t equals to 2. And again, let's try drawing a sign diagram. Make sure that 0, we have 0 here because time cannot be negative. So we have the root 2, and let's try, it's up to you whichever method you use. Let's just do the method graphically. So we know that this is a linear function, and we know that 6 is a positive number, so it's upward sloping. And we have the root at 2. And when is it negative? Well, it's negative when it's less than 2, and it's positive when it's greater than 2. So we have negative and positive there. And there you have it. That's how we draw a sign diagram. Now that we have that, let's try find the initial conditions and hence describe the motion at this instant. So as I wrote here in my worksheet, initial conditions really just means, well, what happens when time is 0. So to do that, we want to know what's happening. We want to basically have s of 0, v of 0, and a of 0. So when we do that, s of 0 is, well, 0 minus 0 plus 0 minus 1, well, that's just negative 1. And remember to always have your units, just to be clear. And for velocity, when t equals to 0, that is 9, right? And for velocity, it's going to be cm per seconds. For acceleration, when t equals to 0, well, when t equals to 0, that's negative 12 cm per, you guessed it right, seconds squared. And if we were to write that in sentence form, well, for the position, we know that it is a negative number, so we know that it's moving to the left. So the particle is how many cm? 1 cm to the right or left? To the left, because it's negative of the origin. And it is moving, is it moving right or left? Well, because velocity is positive, we know that it is moving to the right with how much? 9 cm per seconds. And it is accelerating or decelerating. Well, it's clearly decelerating because it's negative. Decelerating, and we have at a rate of 12 cm per second squared. And there you have it. That's how we put it in words. And for part C, find the position of the particle when it changes direction. So first of all, when you see the word change direction, for example, if I have a parabola, that's our original function. If we want to know when it changes direction, it basically means when is it going from increasing to decreasing or decreasing to increasing. And in this case, it's increasing here. It's increasing. Oh, and then it decreases and decreases and decreases. And we can see that it changes at its vertex. And that's when the derivative is equal to 0, right? Because that's when it changes direction. And so here, the position of the particle when it changes direction, while it's saying for the position, it basically means when is s prime of t equal to 0. And we know that s of t is the same as v of t. So when is v of t equal to 0? Well, we solved here, it's equal to 0 at t equals to 3 and 1. So at t equals to 3 and t equals to 1, that's when velocity is 0. So we want to find out the position. So if we want to find out the position, what we do is we simply plot time back in. So for time equals to 1, we get here 1 cubed minus 6 times 1 squared plus 9 times 1 minus 1. And if we solve for that, we get 3 cm. And we want to plot the second value at t equals to 3. That's 3 cubed minus 6 times 3 squared plus 9 times 3 minus 1. And if we were to do that, we get a value of negative 1 cm. So that's our position. And now we want to draw a motion diagram for this particle. So a motion diagram basically shows when the particle starts, when it ends, and when it changes direction. So the first thing we want to do is draw a line. So we have the values. So it is the position, right? And around to scale, we want to have a distance of like 0, 1, 2, 3. We're just plotting numbers here, right? And now we want to find the position. The motion diagram really just shows the position. So first we want to find out when it starts. When's the starting point? So the starting point is basically the initial condition, right? And we know the initial condition is when t equals to 0. And again, it has to do with position. So when t equals to 0, the position is at negative 1 cm. So where does it start? Negative 1 cm, which is right here. And we can label that when t equals to 0. So now we know that it starts here and it'll keep on going forward, and then suddenly it will change direction. And when does it change direction? Well, we just solved where it changes direction when when the derivative of s of t equals to 0. And we know that it is at t equals to 3 and t equals to 1. So at t equals to 1, what's the position? It's 3 cm. So it's right here. So it's going to go here. It's going to go forward to 3. And that's at t equals to 1. And then it changes direction, right? So it'll go that. But then when does it stop? Well, here we have s of 3. So when t equals to 3, the position is at negative 1 cm. So basically it's going to go back to here where it started. And that's when t equals to 3. And then it will keep going, right? Because that's the idea. The motion diagram shows where it starts and where it changes directions and where it ends. So there you have it, that's our motion diagram. And now we want to find the total distance traveled in the first 3 seconds. So in the first 3 seconds, we want to show the distance. Now how do we do that? Well, here in our motion diagram, we actually already found out when t equals to 3. It does say that the position is at -1, but that doesn't mean that it is the total distance. To find the total distance, we want to see all the way here. From here into here, what is the total distance? So here we started at -1, and then we went on to 3. That's a distance of 4 cm. And then from 3 back to -1, that's another distance of 4 cm. And we stop there because it is asking for the first 3 seconds at t equals to 3. And so our total distance then is just going to be 8 cm. That is our distance. And there you have it. I hope this video helps, and I hope you enjoyed and hope it makes sense. This is the idea of motion. We have s of t, the displacement, v of t for velocity, and a of t for acceleration. And to find that, we basically take the derivative of one another to solve for these values. Thank you again for watching, and I'll see you guys next time.